Download this code from codegive.com, link in the description below. Neural Slicer for Multi-Axis 3D Printing, a tutorial for SIGGRAPH 2024. Introduction. As 3D printing technology advances, the need for innovative slicing techniques has become paramount. Traditional slicing methods often struggle with complex geometries, especially when it comes to multi-axis 3D printing. Neural Slicer is a novel approach that employs machine learning techniques to optimize the slicing process for multi-axis 3D printing. In this tutorial, we will explore the concept of Neural Slicer, its architecture, and provide a code example to illustrate its implementation. This information is tailored for the SIGGRAPH 2024 audience, focusing on both theoretical and practical aspects. What is Neural Slicer? Neural Slicer is an advanced slicing algorithm that leverages neural networks to improve the efficiency and quality of 3D printing. It learns from a dataset of 3D models and their optimal slicing strategies, allowing it to predict the best slicing paths for new models. Key features: adaptive slicing, automatically adjusts slicing parameters based on the geometry of the model. Multi-axis capability, takes advantage of multi-axis printing to minimize supports and improve print quality. Speed optimization, reduces print time by optimizing the tool path. Architecture. The architecture of Neural Slicer typically consists of the following components. 1. Data pre-processing, convert 3D models into a suitable format for input into the neural network. 2. Neural network design, a deep learning model that learns the relationship between the 3D geometry and optimal slicing paths. 3. Slicing algorithm, uses the output of the neural network to generate slicing paths. Implementation steps. 1. Data preparation, collect a dataset of 3D models and their corresponding optimal slicing paths. 2. Model training, train a neural network using the dataset. 3. Slicing generation, utilize the trained model to generate slicing paths for new 3D models. Code example. Below is a simplified example of how to implement a neural slicer using TensorFlow and Keras for a multi-axis 3D printing scenario. For simplicity, we will create a dummy dataset and a basic neural network, focusing on the slicing prediction. Step 1. Install required libraries. Make sure you have TensorFlow installed. Bash. Pip install TensorFlow numpy matplotlib. Step 2. Data preparation. For this example, we will create a synthetic dataset. In a real-world scenario, you would use a dataset of 3D models and their slicing paths. Python. Import numpy as np. Def generate _dummy_ data, number _samples. Generate dummy 3D models, as voxel grids, and their corresponding slicing paths. X equals np.random.rand, number _samples, 32, 32, 32, 32x32x32 voxel grids. Y equals np.random.randint, 0, 2, size equals number _samples, 10, 10 slicing paths, binary. Return x, y. X, y equals generate _dummy_ data, 1000. Step 3, Neural Network Design. We will create a simple convolutional neural network, CNN, that takes the voxel grid as input and outputs the slicing paths. Python. From TensorFlow import Keras. From TensorFlow.Keras import layers. Model equals Keras.sequential. Layers.input, shape equals 32, 32, 32, 1, input shape for voxel grid. Layers.conv3d, 32, kernel _size equals 3, 3, 3, Activation equals reload. Layers.max pooling 3D, pool underscore size equals 2, 2, 2. Layers.conv 3D, 64, kernel underscore size equals 3, 3, 3, activation equals reload. Layers.max pooling 3D, pool underscore size equals 2, 2, 2. Layers.flatten. Layers.dense, 128, activation equals reload. Layers.dense, 10, activation equals sigmoid, output for slicing paths. Model.compile, optimizer equals atom, loss equals binary underscore cross entropy, metrics equals accuracy. Step 4, training the model. Now we can train the model with our dummy dataset. Python. Reshape data for model input. X equals x dot reshape, -1, 32, 32, 32, 1, adding channel dimension. Train the model. Model.fit, x, y, epochs equals 10, batch underscore size equals 32, validation underscore split equals 0.2. Step 5, slicing generation. Once the model is trained, we can use it to predict slicing paths for new 3D models. Python. Generate a new dummy model for slicing. New underscore model equals np.random.rand, 32, 32, 32, dot reshape, -1, 32, 32, 32, 1. Predict slicing paths. Predicted underscore paths equals model.predict, new underscore model. Print, predicted underscore paths. Conclusion. Neural slicer represents a significant advancement in the realm of 3D printing, particularly for complex geometries requiring multi-axis capabilities. This tutorial provides a foundational understanding and a basic implementation of a neural network to predict slicing paths. For SIGGRAPH 2024, we encourage further exploration into optimizing neural architectures, enhancing dataset quality, and integrating with existing 3D printing workflows. As the technology matures, we anticipate significant improvements in printing efficiency and quality. Feel free to explore and expand upon this foundational work to suit your specific needs and applications in multi-axis 3D printing.